My name is Shiva Krishna. We are going to see about the aerospace structural dynamics as a topic of undamped vibrations. Okay. So previously we have been discussed about the what is the different types of vibrations and what is its nature and what is the different types of equations we need to be solved for this one. You can check these previous equations and previous topics in the previous video. So from previous equations version, we have been taken about this natural frequency and force of elasticity and damping conditions. So in this equation, we have been discussed about the summation of forces, which is equals to the response plus system input, which will be going to be input. That is whatever we have been given input, that will be going to be output in terms of with some different motions, as well as some internal energy will be going to be taking place. We have been discussed all those things, and the undamped system single degrees of freedom we have been discussed, and how to solve this all this by using of these equations we have been seeing, right? So today we are going to continue about this undamped system, undamped free vibration system, and how to solve this. So in this content we are going to see about the introduction and determination of natural frequency, what is meant by natural frequency, and damped free vibration and transverse vibrations we're going to see, and what is meant by free torsional vibration also we're going to see. So previously we have been discussed about the what is meant by damping, how it is equation of motion will be works, and how the natural frequency has been derived from this, and what is the conservation of energy have been taken. If it is not taken, that is a free and natural frequencies, natural vibration we have been taken. All these systems we have been seen previous videos. So today we are going to see about the what is meant by undamped free vibrations, undamped free vibration. In this we are going to see about the undamped natural frequency and free transverse vibration, free transverse vibrations in this particular video. Okay, good morning everyone. Once again, this is Shiva Krishna from Institute of Aeronautical Engineering, and this course is for Aerospace Structural Dynamics UG 7th semester. And in this introduction, we have been already seen if the external forces are removed after the giving some initial displacement from the spring mass system. If the initial forces have been removed, then it is trying to regain to its original position. Okay, original position. That is called reaction. That is called reaction. The displacement to the system and to the system of vibrate due to its internal elastic forces. Due to this internal elastic forces, that such vibration is called as free vibrations. That is, we are not going to give any forces when it is vibrating. It has been given previously, and once it is removed, also there will be some vibration is internally with these elastic forces, so that it will be called as a free vibration. And if an external artificial resistance to the vibration, then the vibration is known as undamped system, undamped free vibration. There is no external artificial resistance. Means here in this resistance, if it is not there by any other mode, we can call it as a undamped system, undamped free vibration. So they will be continuously vibrating without any external force, it is to their original position. So here, in the most of this free vibration, always there is a certain amount of damping associated with these systems. So previously we have already seen that when there is a natural frequency, we have been seen once the force is given, it has been given such a large amplitude, and once it is removed, then it is try to reduce like some of the vibrations, right? So it is called as damped vibrations. Like if you turn on the fan and there is a continuously rotating, and if the energy has been stopped and it is trying to go for this state of the static state, right? So it is trying to reduce slow by slow. Within a minute it won't be stopped. At least it will be going to be some stopping with a 1 or 2 minutes it will be taken place, right? Without giving the energy, there is some motion is going to be carried with this fan, right? If you say that there is a motor, also there is a propeller or else rotor, any blades, it will be going to turn some of the time, right? It is having some vibrations in it. It is having some naturally it will be going to have energy into this, right? In this, there is called as some damping associated with this system. So there will be some energy inside. There is trying to reduce their frequency, and it is trying to get their original position like a static state, right? It is called as a damped systems. And however the damping system is small, all particle purpose, it can be neglected to the vibration and considered as undamped system. So will be, however, it will be very small. If you say that there is a very small, and it is called as a practically purpose, and it can be neglected vibration. There is a neglected vibration means there will be no vibration we cannot able to see into this. There is no vibration that we cannot able to see. That is called as a, it is called as damped undamped vibrations only. So here, what is meant by resonance? Resonance is nothing but when the frequency of external force acting on a body, when the force is external force is acting on a body due to this natural frequency. The artificial natural frequency we have already said. Once there is a Fi equals to root by K by M. Root by K by M, we have been seeing the natural frequency, and omega n. Omega n, we have been seeing that is the natural frequency we have been taken. Right? Once equal to this, excitation, external excitation of force acting on a body is equal to the natural frequency of vibrating body. The amplitude of vibrations becomes extremely large. So we have been seeing there is a amplitude, right? So which is into this called as a minimum to 0 to maximum distance. 0 to maximum distance, which is called as a amplitude. Okay, this amplitude becomes excessively large, such as known as a resonance. So, which is once a external forces acting on a body, then equation to the natural frequency vibrating on a body, the amplitude of this one will be going to be very large. So, once suddenly, if the energy added to the system, then it is trying to move to the higher peaks. That is called as a resonance, right? Suddenly, if there is a natural frequency, if it is occurred, then if you give some energy to this particular system, it is giving the maximum of the amplitude. So, if you start the motor, or engine, it is tried to take extra energy, or else if you go for some loading capacity, it will be trying to take as a peak energy to start. Is a motor, or else in the engines also, there will be while starting, there will be having high amount of energy will be going to consume. Though that is called as a resonance when it is comes to this large excitations such as known as resonance. The resonance dangerous, and it may be lead to failure of the parts also one of the times. Once it will be having larger or maximum peak frequency if it is came, and it is having some disturbances into the system. Disturbance once it is comes, there is no problem. If it is comes regularly, then it is try to destroy that particular parts, and the continuous body will be going to destroy later. So there is called that will be having some dangerous to this particular any things. So mostly where there is a maximum frequency is occurring, then we need to try to reduce the resonance by using of this some vibrations or dampers, or else by spring absorption. Anything by using of this resonance we need to be reduced. Right? Resonance we can be give the highest amplitude. Highest amplitude if it is comes, then it will be known as resonance. Resonance nothing but here, if there is a small amplitude is coming, and suddenly if there is excitation, and there will be raising of this amplitude, and again it will be going to come to this naturally. So in this particular side, if you see this is the box, this is called as resonance. Okay, resonance will be going to come when there is a maximum amplitude will be taken place, right? Maximum amplitude will be there, then it is called as a resonance. I hope you are understanding this one. And how to determine this determination of natural frequency? We are having some energy methods and Rayleigh's method. We have been discussed already. Equilibrium method. That is F equals to ma we have been taken, right? So which is x double dash we have been taken already, right? So in this various method to obtain this vibration of this natural frequency of the body, natural frequency of any body of the system depend upon the geometrical parameters. Geometrical parameter means maybe it will be having small or else large scale. We cannot go for directly for the equilibrium equation only. So according to the different size of the particle, like if you go for this small nib or pen cap, if you say there is some vibration will becomes if you drop that, right? Or else if you go for some like a motor, if you say there is it can be able to solve by using of the equation of motion and energy methods. But if you go for this large particle area like rockets, okay, like rockets, or else complete aeroplane body, or else completely if you are having space things like a satellite things, okay, there will be some energy absorption will be there, energy dissipation will be there, and within this energy absorption and energy dissipation there will be some motions will be going to happen, which is having frequencies, right? In these frequencies there will be vibration will be going to cause. So to find out the natural frequency according to the geometrical part parameters and mass properties of the body, so in this mass also there will be having particular role into this because of the density variation, as well as there is a absorption of the material, absorption of the vibration materials will be going to take place. Like if you say there is a sponge is there is also material, right? And there is a steel is there, and there is a like high density material is there, low density material is there. So according to that mass, there will be some vibration free will be there, vibration absorption will be there. So we cannot able to neglect these mass properties. So in this mass properties, which is density will be going to be affect all these things, and geometric parameters, which is having the larger particles or else very smaller particles. Like it may be having some different shapes. If there may be having rectangular, I section, open section, closed sections, which is already we have been discussing the space structures in the 1 and 2 1 and 2 space structures, right? Where is it having the shear center, everything, right? So once we are having the geometric parameters as well as this mass parameters, then we can able to go for these different methods. So it may be a equation of equilibrium method, or else energy method, or Rayleigh-Ridge method. In this popular there is a equilibrium method because it is very easy to solve, we can able to expect the equation within the maybe 2-3 minutes for the who are basically from the undergraduate level and who are in the freshers to the natural frequency and how to obtain all those things. It maybe takes about 2 to 5 minutes for the basic problem, at least 2 to 5 minutes. And energy method may consumes 5 to 10 minutes, and Rayleigh-Ridge method and everything, it may be computerized formless. So there will be FEM. You might know that FEM, this will be ANSYS, and some different applications which is will be giving the some analysis purpose, which is having the large models will be going to discuss into this Rayleigh-Ridge method, because single step we cannot able to solve all the body parts, right? All the body parts have some different mass properties and different variations of this. So in the Rayleigh-Ridge method, we can able to go for this high densities, low densities, and different conditions we cannot able to go. And Rayleigh-Ridge method is going to be especially used in FEM methods. FEM methods already we have been studied, and in this Rayleigh-Ridge method we are going to for especially for the computers, high performance computers will be going to use, right? So energy methods and Rayleigh-Ridge methods will be going to discuss in deeply. In this equation of equilibrium we had already discussed, and how to find the natural frequency also we have been seen, right? How to find the natural frequency, displacement, velocity and amplitude, all this we're going to discuss in this particularly again. So what is meant by equilibrium method? According to this D'Alembert principle, which is already we have been discussed in the previous chapters, previous class also, and a body or a system which is not a static equilibrium. Which is not a static equilibrium means there will be some movement is going to be happening. If the body is having some continuous movement, it is there. Then due to this acceleration, it possesses can be brought into some static equilibrium by equally introducing some inertia forces. If you suddenly give the some stopping of forces or opposing forces, if you given, then there will be inertia is going to be happens. Like if you are traveling on a bus or else on a bike, if you suddenly apply the brakes, then you may feel that inertia. Then you can able to apply this D'Alembert principle. It's some application. So if you give inertia, then you will feel like a jerk, or else there will be some movement has been occurred in your body, right? It is try to move forward and it is try to get back directly, right? It is nothing but some inertial force, right? The D'Alembert principle, that is, it is trying to give some due to some static equilibrium, which is not a static equilibrium moving. Due to acceleration it possesses, it can be brought static equilibrium by introducing this inertial force, right? If you give the internal inertial force, it will be going to be stopped. If you the moment is given, that is the force is already acting on this, and if you introduce the inertia if you introduce, and it is try to stop this by using of some opposite forces, and it is having some static place, it is going to come. This static place it will be going to come when it is called as a static D'Alembert principle. The principle used to develop an equation of the motion for the vibrating system. So vibrating system, when it is having some motions in it, okay, when it is having some motions in it, we need to be stopped that particularly, right? To stopping that, we are introducing inertial systems. What are the inertial systems? Like springs, or else there will be some absorption of energies, and mass balancing. Mass balancing also, it will be having some inertial systems will be going to introducing. So equation of motion for this vibrating system, which will be further used to find the natural frequency of the vibrating systems. If we are finding this natural frequency, we can add so much inertial properties, or else we can able to give some mass to the particular side by side. So then we can able to stop the particular vibrations in a see, there is a pole, large pole, okay, which is having the connected wires like this. Again, there is a like a 200 meters, every pole is there, you can check, right? And it is having some vibrations in it by carrying the current amperes, right? By carrying some high voltage systems, and there is the dampers or absorber will be there. If you try to see that there is a wire is going to be moving. So then if it is moving continuously, then several failures might be occurs. So they have been introduced some of the mass dampers over here at this particular center, okay, that is called as a damper pole. Cable with current. Cable with current. If it is passing, then there is a vibration will be going to come. So it is damper has been introduced. Then there is a drop in vibrations. And it has been given a some small current passing over there. Then it has been stopped. Most of the vibrations it has been stopped, and there is a failure chances are less. The failure chances are less into this particular example. So which is came from this D'Alembert principles only. Once if you give the inertial forces, it is trying to reduce the static equilibrium, that there is a wire has been simply not moving. There is an undamped system we have been taken. Into this example. This is one of the example only. So there is a, if you see the cycle spokes, and there is a most mass moving over there, some different conditions. If you give the dampers, then it is try to bring that original position, and it will be causes simply take the original static position. It is called as a undamped system, bringing back to the static state system by using of D'Alembert principle, right? And you can check this how it will be considered. So here, meanwhile, we are having some spring mass system which is unstrained position. The spring is there and there is a mass has been attached over this spring suspended with the position. Here you can check there is a mean position. The mean position delta has been taken in this spring, which is not given any forces, or there is no unstrained position. There is a force if it is given, like mass if it is attached to the spring and it has been given some distance. There is a displacement we call. Displacement has been occurred because if you stretch the spring by using of this attaching the mass, then it is having some deformation that will be called as a delta over here. And we are seeing this free body diagram here. FBD is nothing but free body diagram, and there is a mass which is having the M representation and which is having the M into G gravity. We have been observed the forces. The mass, it is towards downwards, and K and S. K is nothing but spring force. It is try to get to this original position, right? If there is a spring, it is try to go there original position, right? So it is having the opposite motion, opposite side is there. So we are having the K and delta. K and delta is there. Delta is nothing but deformation, right? How much deformation it is try to reduce? It is try to go for this upside about delta, right? So what is the displacement position? We need to see. What is the displacement position? There is a K is there nothing but spring system elasticity, and the mass has been moved by using of this particular position to this position. That is a positive displacement we have been considered. The positive displacement we have been considered towards the downside, right? In this, there is a x double dash, acceleration velocity we have been taken. Distance is the x, acceleration is nothing but x double dash, and velocity has been taken. Distance, acceleration, velocity we have been taken. X dot and x double dot we have been taken. And spring forces will be taken as K into x plus delta. K into x plus delta we have been taken. Delta is nothing but displacement. Okay. K is the spring force. Spring force, which is nothing but we have been taken x plus delta. X is nothing but distance, that is try to move to this distance, right? This much acceleration we have been taken, distance we have been given, the positive displacement downwards has been given. So it is try to move to this particular original position. And there is a motion of the body. There is a motion of the body will be going to be towards the downwards. Towards downwards, there is a motion of the body will be going to come towards the gravity. So gravitational forces and mg is the mass momentum we call. The mass is going to be towards the downwards because there is a gravitation pull is going to be occurred, right? We already know from the 8th class onwards, there is the Newton's law. It is try to pull whatever the body is in the sky or else there is a height. It is try to move towards the earth, right? There is a gravitational force is going to be captured towards there. And m is the mass, which is gravity has been towards the downwards. And inertial forces we have been taken as m into x double dot. X is the distance, x dot is the velocity, m x dot is nothing but acceleration, which is nothing but F equals to ma we have been taken. F equals to ma has been taken. What is F here? There is a mg. The force is nothing but mg has been taken, and m is nothing but mass, and a nothing but acceleration. A is nothing but acceleration. Acceleration in terms of x we are calculating. Acceleration in terms of x is nothing but d by dx square. This d by dx square acceleration is going to happen. So simply we can able to write it as double dash, right? X double dash we have been taken into this particular picture. So this is nothing but equation of motion and equilibrium method. Equilibrium nothing but there is a force which is equal to the mass into this equal into acceleration, right? So in this, inertial force is nothing but mx double dot, and spring force is nothing but k into x plus delta, and gravitation force is nothing but mg. So according to the D'Alembert principle, sum of the inertial forces plus external forces should be zero. Like we have been taken F equals to ma, then D'Alembert principle is saying that in this, inertial force is nothing but here F plus ma. So F plus ma will be zero. In this, F minus ma will be going to zero. The forces which is given. Internal forces F equals to zero. Right? Internal forces which is inside the position plus external forces. Whatever the forces, whatever the external forces is given, that should be equal to zero. Whatever the force is given and how much energy has been observed, which should be equal, then only it will be going to be zero, right? So in this, D'Alembert principle is saying that inertial forces plus external forces, there is a minor forces will be going to be observed into this particular system. That will be maybe as friction, or else there is a heat transfer or conservation of energy, we call it as. There is a minute energy losses. So we cannot able to exactly say that this is how much conservation of forces have been occurred. So that will be going to be neglected forces will be taken. So it will be going to be inertial forces plus external forces will be going to be zero. So mx double dot plus k into x plus delta plus mg. So which is acceleration, which is inertial forces, plus external forces is nothing but m plus g, m into g, right? Internal force is nothing but m into a double dot, m into a plus distance, k movement, right? Spring distance, and plus mg equals to zero. We can able to write it as in terms of x double dot plus k by m, delta we have been taken outside, right? M into G we have been taken outside, zero. So G is constant over here, right? G is constant, we can able to take it as 1, and delta is also we can able to say it as there is a constant value. So values which is having there, then we can able to make it some simpler one. So into this, x double dot m has been taken outside, in this m has been taken outside, and m has been already moved to this right side. So x double dot plus k into k by m. K by m has been taken into this. So k has moved to this here, right? So which is nothing but x double dot plus k by m, which is going to be zero, which is given into this equation of equilibrium. Method. So comparing the above equation with the fundamentals of equation, simply harmonic equation of equilibrium, we can able to get it as x double dot plus omega n square into x, which is called as a 0. Omega n, we already said that there is a under root of k by m, right? So which is we can able to write it in terms of k omega square, which is omega square actually, right? So we can able to write it in terms of omega n equals to k by m under root of k by m, right? So Fn is nothing but natural frequency. We can able to write it as omega n, omega suffix n by 2 pi. So which is we are replacing with the terms of k by m, which is in terms of which is natural frequency, right? So natural frequency equation, how it has been derived, we have been seen from some example of spring mass system suspension, which is F equals to ma. So in this, some free body motion has been occurred, and if the mass is given, there is a reaction forces we have been calculated, which is x dot and x acceleration, distance, velocity, and acceleration. Okay, distance, acceleration, velocity has been calculated. Into this, force D'Alembert principle has been given as a sum of the inertial force plus external forces equals to 0. Right, inertial forces, external forces will be going to 0. From this, we can able to write it all this equation with a natural frequency, right? So next method, The next method is nothing but energy methods. You may already learned about these energy methods in previous aerospace structures. Structures 1 and structure 2 we have been already discussed in previous chapters. Okay, previous lectures. Okay, if you don't know, please again go read that particular basics. You may get some of the information which is like what is meant by energy and how to convert particular point and 2D, 3D and how to calculate all those things. We can able to write it all those into these energy methods. In this, according to the law of conservation of energy, energy can neither be created or not be destroyed, but it can be transferred from one form to another form. You may already learn all these equation, all these energy methods into the 8th class, 9th class, but we are into this application method. You may learn that equation into the 8th class, 9th class and 10th class, but you may not know that how it has been utilized into the particular physics way as well as applications, right? So we have been under the application point of view. So it is a definition only, the conservation of energy, which is can be neither created or not destroyed, and it can be transferred from one particular point to the another point, right? It's a transformation of energy only. They will be not going to be destroyed or not going to be created, right? Like a cycle, has a cycle. So like a cycle, it is going to be taken place. So there will be some energy has been converted to this another particular energy, and it will be create some another energy. So it won't be destroyed anywhere. So in free damped vibration, no energy has been transferred into the system or to the system from the system. We said there we have been already given some free vibrations. There is a force has been stopped. Force is not there. Force is not there, right? So energy which is not going to transfer into this. So in this, no energy has been transferred to the system or from the system. Therefore, the total mechanical energy remains constant. So the force is not given, then energy into this, energy is constant. Energy is constant, right? We need to go to that. There is a free damped vibration means energy is constant. Free damped vibration means the energy is constant. There is a particular way to remember, right? And in this, there is a kinematic energy due to the motion may be occurred, or else potential energy due to this gravitation pollutions energy, or else strain energy. Like if you give the some kinetic energy due to this motion, there will be body maybe happens, energy, different energies, and gravitation pull also may be occur, strain energy will be going to be occur if there is a height is given, potential may be given, or else gravitation force will be given into the system. At the equilibrium position, kinetic energy maximum. At the equilibrium position, kinetic energy is maximum and potential energy is zero, vice versa. So potential energy will be going to zero and kinetic energy will be going to be zero. When it is vice versa, it is going to come. Like if we are giving, keep on reducing and keep on giving this, there is a vice versa will be going to happen. According to the law of conservation, total energy will be going to constant. Then total energy, kinetic energy plus potential energy will be going to be constant into this, which is undamped system, right? In this free damped vibrations, undamped systems only, right? So in this, how energy methods will be going to take place in definition. Differentiating this particular kinetic energy plus potential energy equation 0, which is kinetic energy, we can able to write it as half into mx square, which is half into ma, right? mv square, half into mv square. We have been already seen that there is a kinetic energy is motion, right? Which is having the motion into this, half into mv square. V is nothing but, here it is, V is nothing but, we are taken in terms of x dot, right? X dot we have been taken. It is a velocity. Distance we have been taken x. Acceleration we have been taken as x double dot. Right? Acceleration we have been taken as x double dot. And potential energy we can able to write it as half into k x square. there is this power, there is a power, okay, half into k x, k is distance square, k square, right? S is nothing but distance we have been taken. We have already seen that some of the physics equation, how much distance we have been taken in terms of S we have been taken. So half k square is nothing but potential energy we have been taken, right? Substituting all these equations into this previous equation, that is the kinetic energy and potential energy we have been taken 0, and we can able to get it as x double dot plus km, k by m, right? K by m will be going to be 0. Comparing the fundamental equation from the SHM, simple harmonic motion, we can able to get it natural omega, that is fundamental equation, natural frequency, we can able to write it as in terms of k by m, under root of k by m. Natural frequency, we can omega, we can able to write it, okay. Natural frequency will be called as in terms of omega n by 2 pi, right? Omega n by 2 pi. So in Rayleigh's method, there is an external energy method which is deployed by this large Rayleigh. So total energy will be going to be constant to this. Kinetic energy plus potential energy, which will be going to be kinetic energy plus potential energy in position 2. So it is in position 1, first position, it is in second position. So there is a movement has been occurred, first position to second position, like a body is moving towards some destination, and it is having some motion with acceleration, or else there is a Rayleigh's method, there is a displacement is going to be occurred. Displacement is going to be occurred with the forces, external forces applied. Then there is a kinematic energy will be going to change. There is a position kinematic energy and potential energy is going to be changes according to this Rayleigh's method. So subscript 1 and 2 differences the positions, and let 1 is subscribed the mean position with the potential energy is 0. 1 is at this potential energy, at the particular position, kinetic energy will be taken as 0. Okay, kinetic energy particular position we have been taken 0, and subscript 2 denotes the extreme position where the kinetic energy is having 0, where the kinetic energy is 0 into this particular 2 position, right? So in this above equation, kinetic energy equals to potential energy we have been taken. Because it is moving body, Rayleigh's method, we can able to say that there is a key points we have been taken as a potential energy has been taken once, and again there is a kinetic energy has been taken once, right? So which is Ke maximum and Pe maximum when it is comes to the second position to first position, because if it is moving from one position to another position, the moment should be there, means there is a complete forces, maximum force should be there. So there is a kinematic position should be maximum, and position second, there is a positionally it has been moved already. The force is unable to move there particular one position to second position. There is no energy has been observed again. There is second position, there is no energy to remains. Like if you go for this sudden absorption of energy, if you give the bending force to this cantilever beam, if you give the motion, there is a kinetic energy has been taken at the particular position first, like in this particular way. So in this position, kinetic energy we have been taken max. Kinetic energy is max, and into this potential energy is max. If you give the load into this, kinetic energy has been taken maximum, and potential energy has been taken as maximum at this particular position 1 and 2. Position 1 and 2 we have been taken into this Rayleigh's method, which is energy at this mean position will be equal to the maximum potential energy, which is extreme positions, which have been taken into the next levels. So there is a Rayleigh's method is saying that let the body is moving in a simple harmonic motion, therefore displacement of the body is given as x. Displacement is given as x into sine omega t. X into sine omega t has been taken as a displacement. Okay, displacement as x, and differentiating this x equals to sine omega x and sine omega t, we are in terms of x displacement differentiating, that is called as velocity. Velocity we can able to call it as dx by dt. Dx by dt, if you say there is a omega n x capital X, which is cos omega nt. So here there is a sine has been only diversified, and there is a omega t which is constant, so that's why we have been taken to this chapter to this, right? So omega n we have been taken first, so constant we have been taken, there is a constant will be going to happen, and again sine has been converted into this cos, cos converted into sine, sine has been converted into this cos again, omega n t. So x maximum, what is the x maximum? Velocity maximum which will be omega n t, which is at the time of 0, which is position, mean position, we can able to say the mean position. And where the maximum kinetic energy will be going to occur, the Ke maximum at this half of mx double dot, mx max, half of m into x dot, which is velocity maximum square, velocity maximum x distance square, and kinetic energy maximum we can write it as into this half into m omega n x whole square, which is power. Okay, maximum potential energy extreme position will be taken into this half into kx square, half into kx square we have been able to take it, half into kx square or else ka square. Okay, acceleration, right? Comparing the both equations, we can able to write it as a omega n is nothing but k by m half under root of k by m only, which will be constant everywhere, it will be constant, and omega nt is nothing but natural frequency for this Rayleigh's method. Omega n 2 pi, omega n, sorry, natural frequency we can able to write it as omega n by 2 pi, right? So to this we're going to stop, and we're going to see about the undamped transfer system into this next classes, right? What is an undamped system, how it will be going to take in place in this cantilever as an example, all those things we'll be going to continue in the next classes. Okay, thank you all.
Like, share and subscribe. Hit the bell icon for more updates.